Well, the potential energy change is the delta Y multiplied by the weight. The weight is 1.96 newtons. You multiply that by 0.8 centimeters, and you get, well, it's going to be about 1.6 newton centimeters, which is about 0.016 joules. Now, doing this exactly because we want to do a comparison with the exact results, this is actually 0.01568 joules, and I think that's correct, but again, done mentally. Kevin's mental calculation agreed with mine, so I think it's probably right. We both wouldn't be wrong at the same time. I'd be more likely to be wrong than he would. Okay. And as you know, I'm not all that unlikely to be wrong. Okay. At 4 centimeters, we do the same calculation. We're going to do the x squared over 2L, which is what we used up here. And we would get this. Now, we can get this just by proportionality. This is half as great as the 8 centimeters, and we're squaring it. So when we square something that's half as great, we get something that's a fourth as great. And I actually calculated this by taking a fourth of this. But it has to be that. And then this is half of this, so this is going to have to be 1/4 of this for the same reason. So I think these results are correct. You can calculate them any way you want. You should probably try to calculate them every possible way, using every possible shortcut, and see if you get consistent results. Now remember, these results depend on this approximation, so they're not exact. And I got a little confused in class when the actual precise result that we calculate here based on the integral and everything did exactly match this, because it shouldn't. And I just kind of lost track of the fact that this was the approximation. So I'm going to warn you against that assumption. That won't necessarily show up here. I didn't have to point that out, but I think there's a lot to be learned from watching my bonehead mistakes, as long as they don't get too distracting, and many times I know they are. Okay, the potential energy change from 0 to x is what? -1/2 the integral from 0 to x of negative k times the dummy variable we use instead of x, because we're using x on the integral. And this dummy variable is this fancy Greek symbol here. I won't even tell you what it is because I'm not completely sure. Is it upsilon, xi? I think it's xi. Doesn't matter, whatever it is, when we do the integral, we get -1/2 k times that fancy symbol squared, and then we plug 0 and x in, and we get 1/2 kx squared. That's the change in potential energy. Now I have here 0 to x. Don't know if you can read that. So when we move the thing from position 0 to position x, the restoring force, which is conservative, it's a component of the gravitational force, is -k times the displacement. And this fancy Greek signal stands for the position. Okay, so it's the position relative to equilibrium, which is then the displacement. This integral would give you the work done by that conservative force. Change in potential energy is equal and opposite to the work done by conservative force, which is the definition we use in this course. And I think it maybe is a good definition to use if you keep it in mind, because you don't get confused about the sign of the thing, at least not as badly as you might get confused if you think about the definition of potential energy by something that's unconnected. Okay. Again, your own taste. You can, as long as you get it right, it's okay. But I kind of advocate this. Okay. In any case, the change in potential energy from 0 to x is 1/2 kx squared. Now, I only talk about change in potential energy. I don't talk about the potential energy until I've talked about the change in potential energy, because the potential energy depends on your reference point. Having calculated the change in potential energy from equilibrium, the 0 position, to the x position, it now makes sense to define the potential energy relative to the equilibrium position. And we do that by saying, okay, now the potential energy at equilibrium is 0. Therefore, because the change in potential energy from 0 to point X is 1/2 kx squared, the potential energy relative to equilibrium is 1/2 kx squared. Okay, so now that will be the potential energy of the pendulum, but we are aware of the fact that that is in reference to the equilibrium position. That's the only reasonable position to use for reference point when we're talking about simple harmonic motion. And that would apply to a spring as well, the equilibrium position of the spring. Okay, well, for the pendulum then, our K is mg over L, as we saw in preceding classes. And mg is the weight of the pendulum, 1.96 newtons. That's just the weight of the pendulum, divided by the length, 0.4 meters. Remember that this all came out of looking at some similar triangles, and it's really a very straightforward calculation to see that this should be mg over L. And you should be aware of that. In any case, whether you use this or actually reason it out, which I advocate, you get 1.96 newtons over 0.4 meters, 4.9 newtons per meter. So the potential energy at the 8 centimeter position is what? It's, well, 1/2 kx squared. Now we know K, we plug it in, and we square our x, and we get this, and it comes out the same as the small angle approximation as it does for the small epsilon approximation. Okay, if you multiply this out, you get this. Now, if we want the actual delta y, we have to actually calculate the 40 centimeters minus the square root of the 40 centimeters quantity squared minus the quantity 8 centimeters squared. We get 40 centimeters minus the square root of 1,536 centimeters. This being very easy to calculate in your head, and you should, just 1,600 minus 64. And then, taking the square root, well, yeah, you go ahead and use a calculator for that. And you get, because we want an accurate approximation here, and that's perfectly appropriate, we get 0.808 centimeters as opposed to the 0.8 centimeters we got from our approximation. Note that that's 1% different than that. And since our change in potential energy is just going to be this quantity times the weight, the mg, we're going to be 1% different on our potential energy. And we're going to get this rather than this. And there is a difference of about 1%, and now I'm seeing 15695. Yeah, okay, that's good. Yeah, it's a difference of 0.0000015 from this, 0.0000015. Yeah, and that's 1% of 0.0156. Okay.